yeah, a quick note, we're being live streamed, so that's why we have this. So yes, welcome everybody again. We'll start from the top. So Scroll is a zkEVM project where we're a layer 2 solution for scaling Ethereum. And we're bytecode level equivalent, which is really exciting. And part of our vision and goal is to create an experience that is as close to the EVM as possible. The Scroll team we're super decentralized, we're spread around the world, and we're getting close to almost 40 people now. And going forward, we're looking for more people to join us, particularly if you're creative in nature and have a track record of innovation and have strong execution skills and have exceptional communication skills. We want to hear from you. Not a big ask. So we have a job board on the website, and we'll talk more about that later. So a little bit of high-level introduction on how and why we started. So before founding Scroll, I've been working in the industry for a couple of years. And over the last few years, we've seen an exponential growth in the number of active users, as well as the number of creative applications in the space. So when you look at one simple metric, the number of active monthly users, it was just a few 100,000 just a few years ago, and now we're looking at 30 million active monthly users for MetaMask alone. And with that level of adoption, scaling has become a major bottleneck for the industry to grow. And it has given rise to this problem for a while, and we think is really needed to support increasing demand from innovators and for users around the world. And without scaling, application layer innovations will also suffer. I think in the last couple of years, I think we saw a huge kind of burst of innovation with the beginning of the DeFi summer, but I think that level of incremental innovation has really slowed down, and part of the main reason is because of the scaling problem. So when I met Ying and Haichen, 2 years ago, I think we saw that this problem existed in the space, but at the same time, there was also a ton of innovation that happened in the academic space that we thought we could leverage to solve this problem. And I thought, Ying and Haichen were both very, very value aligned. We all want to build something that could be used by real users, and we want to build something for the long term. So with that clear value in mind, we set about this task of building a team and also building a product that can translate very theoretical research into practical and usable and also user-friendly products. And that brings us to the demo that we're about to see today. So we did a lot of research, and so a little bit about what we care about as a group of people. What is Scroll, and what does Scroll stand for? I think one of the core things about who we are is that we really care about innovation and creativity, and I think these things are not stressed enough in our industry. It's part of the DNA of Scroll, and we want to foster our space and foster this kind of culture within us so that it could permeate into the wider developer community as it builds around us. So we see a future where Ethereum wallets will be owned by everybody on Earth, and in order to make that a reality, I think a ton of creativity and serve it like value creation attitude is needed. And we've always been open source. It's partly about the way we were organized and the way Scroll started, and we've always been collaborative in culture. And I think this has fed to a very open and transparent as well as collaborative building process that speaks to our design choices as well. And I think as a result, we've had a lot of positive academic feedback and feedback from open source developers around the space. And I think that's the way we can generate even faster innovation in the future. And the last part is integrity and intellectual honesty. We do want to make sure that our users think of the brand as one that delivers on its promise and is not overclaiming and is very, very accurate about what we plan on achieving and what we've done so far. So thinking long term, so we're very long term oriented, and so when we see reactionary kind of regulation or things that are happening in the industry, we try to think about how we can position ourselves in the long run and not be too reactionary to short-term impacts that the whole industry is facing. But as a part of that, we do want to have an open call to form working groups to think through some of the aspects of decentralization and how we can build a wider Ethereum ecosystem where there's no single point of failure, and how we can articulate part of this kind of technology will achieve on the social layer to policymakers as well as regulators around the world. So what Scroll is about, we're about kind of innovative thinking and thinking about human, kind of mapping the human into some of the human interactions on chain and delivering very serious academic research and implementing it. That's the whole kind of Scroll design and organization process, which requires immense effort and a lot of help from all of our community members and also all of our contributors. So going forward, we're going to kind of move our mindset to a little bit about growing the ecosystem. So about bringing more users to space, bringing more developers into space, and fostering more application layer innovations and enable user adoption. So with that in mind, if you like what we do and the way we think about organizing the company and organizing our ecosystem, please apply through our website, Scroll Foundation. And in particular, we're looking for people who are very good organizers and strong communicators and who have passion for the technology that we're building. We're looking for PMs in particular, and also there's an array of researching roles and engineering roles all advertised on the website. So with that note, I'm going to hand over to my co-founder, Haichen, to talk about the Scroll architecture and design choices.
Should I click here? Okay, cool. Yeah, hello everyone, I'm Haichen Shen. So before I go into our talk, I just introduce a little bit on our program schedules. You already have the schedule program on your hand. So Sandy just gave an introduction to the Scroll. Next, I'm just going to talk about our infrastructure designs and a little bit of our testnet, and I was just trying to do a live demo. And after that, Ying, Tong from the ZCash, they're going to talk about the programming in the Halo 2, and then some latest progress what happens in the Halo 2. And then Mason is going to talk about our zkEVM architecture and how we build and construct this zkEVM. And then after the break, I'll come back and talk about some performance optimization we have been done for the zkEVM. Okay, so let me get started. And also, we don't just want to this be a very formal presentation, so you can feel free to ask me, break me, interrupt me with any questions. I will be very welcome. So, okay, so I'm going to talk about our Scroll's architectures. Yeah, just one sentence to summarize what Scroll is building. Scroll is building a EVM equivalent of zk rollup solution layer 2 chains to scale the Ethereum and then to bring allow more transactions and lower transaction gas cost for the Ethereum. So we can bootstrap next billion of the users. And then before I dive into some technical details and then our architecture designs, I just want to first talk about our design principles that drive the decision of our design and why we choose this approach we want to build. So there's 4 principles, and the first and foremost, which is the most important things, is what we believe that ensuring the user security should always comes first. And then for Scroll, this means that the layer 2 transaction should have and share the same security level as the transactions that happen in the Ethereum today, and then without trusting even the layer 2 operators. And then we should, during the design, we should never trade off any user security for any efficiency or any other the reasons for that. So just need to guarantee the user security, user can always maintain the access to their funds on the layer 2 or layer 1. And then second, we think an effective EVM equivalent solution, an effective Ethereum scaling solution should allow users and developers a smooth path, a seamless migration path from the existing dApps and then existing developing tools. And then we believe that maintaining the EVM equivalence is the best way to achieve this goal. And then third, the decentralization is one of the key aspects of the blockchain. Usually it's like the overlooked or improperly traded for some efficiency reasons. But we think like decentralization is one of the key property and that we should maintain even at the layer 2 context. And then so like in the scroll, and also the decentralization can guarantee a protocol to be very resilient to any censorship or coordinate attacks. Now like in the scroll, we consider the decentralization across many different aspects and then different layers, including the sequencers, the provers, and then the community of users and developers. And then fourth, for a user to enjoy a great user experience on the layer 2, so believe like there's two important things we need to achieve. One is that the transaction fee on the layer 2 should be way cheaper, like orders magnitude cheaper than the base layers. And then the second is that users should experience some instant pre-confirmation on the layer 2s and a reasonably fast finality on the layer 1s. So this both like requires a good efficiency you can achieve in the layer 2s, so that like to be able to have a great user experience. Now next, let's take a look at see like how we use these like design principles to guide our decisions in our approaches. So first, ensuring the user security and then maintaining the EVM equivalence lead us to a zkEVM based zkROP solutions. So first, the zkROP is like the best. It's guaranteed like a very great security by relying on the mass and the zero-knowledge protocols on the behind. And then the zkEVM, which achieves the EVM equivalency, is the holy grail inside the zkROP solutions. And then it can maintain the EVM equivalence, meaning that all of the user experience and the developing tools will be just directly compatible with the layer 2 when you have the zkEVM. And then zkEVM, because it's a zkROP solution, so you still have to share the security guarantee from the zkROPs. And then second, the decentralization leads us to design a decentralized approval networks. So when we start like designing the zkEVM solutions, we quickly realized that putting the Ethereum virtual machine into the zk proof will lead to resulting a great overhead for generating the proofs. So in order to reduce the time to finality on the layer 2s, we decided so we should build a decentralized prover network that's going to help us to generate the zk proofs. So there are two main benefits for having a decentralized prover networks. So first, the community, like whoever can, we have like if we because we have this seamless, this permissionless decentralized prover network, any community member can come and run a proven node, and then the community will be incentivized to build a better, substantially better solutions, including like both hardware solution or software solution to boost up to help reduce the proving time, so that we can have better solution for to generate a zk proof. And then second, when we're designing our proving infrastructure, we make sure like it's highly parallelizable, meaning that if we want to scale up, we can very easily scale up by just simply adding more prover nodes into our network, so that I can have like achieve very great throughput for generating the zk proofs. And then third, so for the efficiency, so to improve the efficiency of the layer 2s, so our approach is to leverage all of the innovative research-driven solutions across all of the community. So our zkEVM designs takes advantage of like many recent breakthroughs in the including the zero-knowledge proof systems, and then the proof aggregation, and then the very like innovative hardware acceleration solutions. And then second, so we also focus on like to develop in the open source manner, so that this allows us to collaborate with a lot of open source communities, including the PSC team from the Ethereum Foundation and other open source collaborators and contributors. And then we believe that like all of the community contributed to this like open source approach, so can lead to a best and then most effective and efficient solutions for the zkEVM and zkROP. Okay, next I'm going to talk about the Scroll architectures. So first, I was just going to talk about like the basic like modules and components that happens inside the Scrolls architecture. So first, you have like layer 1 chain, which is the Ethereum, and then the layer 2 is the Scroll chains. So in the Ethereum, there are mainly two parts. Like there's two contracts deployed on the layer 1. One is the bridge contract for mainly for bridging any assets or like relaying any messages between the layer 1 and layer 2s. And then actually, like this bridge contract will be also, there's one part of bridge contract deployed on the layer 1 and one part will be deployed on the layer 2s. And then the second contract deployed on the layer 1 is the rollup contract, which we're going to accept the state availability transactions that are going to include some block data and the transaction data inside the rollup contract. And also it include a solidity verifier to verify the ZK proof that are going to be sent to the Ethereum for the finalized any blocks. And on the layer 2, the main functionality is coming from the scroll node, which is responsible for generating layer 2 blocks, accepting RPC requests, and also like relaying the messages, and also generating the proofs. That will be all like happens in responsibility for the scroll node. So inside the scroll node, there are 3 modules mainly. The sequencer is basically just processing the layer 2 transactions and generate layer 2 blocks, also processing any RPC requests. So our sequencer implementation takes a fork of the Go Ethereum implementation with some minor tweaks for the layer 2 purpose. And then because like the Go Ethereum is the most popular execution client for the Ethereum node. So like by directly forking based on the Go Ethereum, so that gives us the best compatibility with all of the existing tools, and then all the RPC interfaces will be the same as like when you interact with the Ethereums. And then second, inside the scroll node, there's a relayer which is going to monitor all of the smart contracts we deployed on layer 1. For example, if find any deposit event happens on the bridge contract, is going to relay this deposited message to the layer 2s. And also the relayer will be responsible for submitting any roll-up contracts, roll-up data to the rollup contract. And then third, there's a coordinator here inside the scroll node. The coordinator is going to watch for any new blocks and getting the execution trace from the Go Ethereum. And then once the coordinator receives a new execution trace for a new block, they're going to dispatch this execution trace to one of the rollers inside the roller network. And then just ask the roller to generate the ZK proofs. And then the roller, then if it finishes the ZK proof generations, it'll just send it back to the coordinator, and the coordinator just will relay that to the relayer for the roll-up to roll up the validity proof. And then inside the roller, so we can talk about the roller as well, because the roller is mainly contact with the coordinator. So the roller is basically running a zkEVM inside. And then we also expect like the roller to be run on a hardware accelerators in order to reduce the time to generate a ZK proof. Because the zkEVM is quite like heavy ZK circuits and very complicated, so it's somehow like if you use the accelerators, you can be like reduce the total time to generate the proof. And then right now we are using a GPU prover to generate the proof, but we expect like the community and new hardware companies can come up with new accelerators can further reduce this proof generation time. And then all of rollers are basically is a prover node. And then we have like this decentralized prover network which is run by different community members in the future. Any questions so far? Okay, so we can like also take a deep, closer look into what happens inside the roller when you're generating the proof. Because like it's also just not very simple, just running the zkEVM. So first, the roller will receive this execution trace from the coordinator. And what's inside this execution trace? It includes the following things. First, it has the execution step when you execute transactions inside the Ethereum virtual machines. For example, you will execute all of different opcodes like add, multiply, or like push and pop to the stack, and then read or write to the memories, and then including also like you're getting any block informations from the block headers. And the second thing, like it will include the block header and the transaction data that are going to be the input to the execution trace. That when you need to get any information from the block header, and also what transaction data, like core data you have. And then third, we also need to load all of the contract bytecodes to make sure that we are actually executing the bytecodes actually from the deployed contracts, not like from arbitrary opcodes. And then last is there's some Merkle proofs. They're going to prove help you to prove the Merkle tree transition from the old state root to the new state root. And then after you the roller receive this execution trace, it will just hand this execution trace to a module called circuit import builder. This circuit import builder is going to transform all of the trace output from the Go Ethereum and then assign into the certain circuits, and then which is like would be a 2D giant matrix. Probably you'll get more idea like after Ying, Tong, and then Mason talk about more about Halo 2. So I'm just going to have like this a few giant two-dimensional matrix, and then you're going to expand all of the executing trace, and then also generate some auxiliary data that helps to generate the proof, and then fit into all of the witness of in those circuits. And then next, when we talk about zkEVM, actually it's not a single circuit. It includes like a set of circuits that works together to generate the proofs. So because like if you have everything inside a single circuit, then it will lead to a even like greater overhead. So that's why we separate them into different parts of like circuits, and then connect them through some lookup tables, which I think Mason will talk more about that in his talk. So this gives you some flavor of those what circuits inside the zkEVM. There's like an EVM circuit. It's the main core circuit that proves the transition of this virtual machine state from the previous step into the next state by applying some of the opcodes. And then this RAM circuit was going to constrain any read-write operations happens inside the Ethereum virtual machine, including the stack push and pop, the memory read and write, and then the storage modification. And then the storage circuit is actually another auxiliary circuit that's going to prove the state transition using the Merkle proofs we talk about like in the execution trace. Apply those Merkle like the proofs like for every change, like including read and write on top of like the inside the storage circuit that can prove the state root is actually transited from the old one to the new ones. And there are also a few other auxiliary circuits I won't just talk about here in this talk. And after you run all of the circuits, so each circuit will actually execute one proof. So there will be like a bunch of the proofs you collect from executing the zkEVM. But if you're uploading all of the circuits into the layer 1 and then like validate them one by one, then it definitely will be resulting in a very large gas cost in the layer 1. So in order to reduce the gas cost for the inside the layer 1 verification, so we need to further using an aggregation circuit that aggregate all of the proofs from the zkEVM and then into a single aggregation proof. And then here we just call it a block proof, which corresponds to a single block. So the aggregation circuit, what's inside the aggregation circuit is it just replicate the verification logic and then just represent it inside a zk circuit so that it can be redo everything like you need to do inside the verifier, and then you can do that inside the circuit. So that would be, and then you'll generate a new proof that's going to, once you verify this block proof, you just basically verify all individual proofs inside the zkEVM circuits. Okay, so this is what happens inside a single rollers. But like usually it takes longer time to generate a single zkEVM proof for like than generating a block. That's why like we will have multiple rollers that's going to run in parallel to generating the block proof for different blocks. And then if you want to further reduce the overhead of the verification on the layer 1s, so you can reuse this aggregating circuit and then to aggregate those block proofs again into a single proof, so that you can only use verify a single aggregation proof that can verify all of the blocks inside in this aggregation proof. Okay, so previously like this, I just described all of the modules inside the ZK inside our architecture. Next, I'm just going to show up like how that works in actions when to do inside the ZK ROP. So in the ZK ROP, like the overview is like you have two chains. One is the Ethereum chain, and one is the layer 2 chains. Here is a scroll. So the layer 2 chains can generate more blocks than the layer 1. So like one layer 1 blocks, maybe you can within that time period, like 15 seconds or 12 seconds after the merge, and then you can generate multiple layer 2 blocks. And then what you're going to do is like you're first going to aggregate all of the blocks within that time or period, and then can just send up all of the data, like the block data or like transaction data, and then roll up like send to the next blocks inside layer 1s. And then like after a while, because the proof generation takes a longer time, then you can have like an aggregation validity proof that aggregates the previous batch of the blocks, and then can send that proof into even later blocks inside the Ethereum. And then after that, the block basically can be finalized. So with that, you can actually have the different status of the layer 2 blocks. So first, initially, the block, once like a block is proposed by a sequencer and included in the layer 2 chains, we call it a pre-committed status. So when a block is pre-committed, it's still, so like this block is not a like canonical part of the layer 2 chains because nothing has been settled like or sent to the layer 1s, but you can still do some actions like optimistically on top of the pre-committed blocks based on layer 2s. And then second, so once the block is generated on the layer 2, so you can collect all of the data you need and then just send that, post it to the rollup contracts on the deploy on the Ethereum. And after that transaction is committed, is confirmed, then this block can be transited from the pre-committed status to the committed status. And with that, you have more confidence because the data of your transaction means like it already be written to the layer 1, so no one can modify that again. So it just only seems like it's not sure if that committed status is, you're not sure that your transaction has been executed correctly on the layer 2s. So in order to finalize a block, you need to then use the zkEVM to generate a validity proof of all of the layer 2 blocks and then all of the transaction like steps that happen. And then you send that validity proof to layer 1 and then be verified by a verified contract. Then that means like this block has been finalized and then that block has been finalized as a canonical part of the layer 2s. So to like see like more concrete example like in the context of a scroll. So first like you have a block generated by the sequencers and then you will roll up the data from this block and then send up to the rollup contract. And then after this block has been confirmed, transaction being confirmed, then the block status should be changed from a pre-committed block to a committed block. And then meanwhile, you also will extract this execution trace from this block and then send that to the coordinator and then being forwarded to one of the roller for the proof generation. And then you can do that for every like the new blocks you get. And then you like there are multiple rollers is going to generate the proof for each block. And then after a while, the coordinator will collect a few the block proof from those different rollers together. And then you can further create a special task with all of the block proof and then send to another roller for this aggregation proof generations. And then after that, the proof generation, the aggregate proof generation has been done. You receive this aggregation proof. And then you can roll up, send that proof into the layer 1 roll up contracts. And then that verification contract will take all of previous data, like you roll up to the contract as the public input to this verified contract so that you can then finalize all of the blocks that be included inside this aggregation proof. Okay, so I'll probably quickly go through like how the bridge works. It's like I think running a little bit late, but I think like that. So how does bridge work is it's quite standard for the layer 1 to layer 2 transactions. So the user just interact with the bridge contract inside the layer 1 deployed in Ethereum. So you do call like deposit token function inside the bridge contract, and then that bridge contract will just emit one event inside the bridge contract. Say like someone just deposited some tokens, and then the layer 1 bridge contract will just freeze this the token, whatever token user transferred to the layer 1 contract, and it'll just freeze inside that contract. And then the relayer will just monitor all of the events generated from the bridge contract, and then wait for a few confirmations on the layer 1s. And then after that, it will just then send the transaction to the send a new transaction in the layer 2 bridge contract. And that bridge contract will then either mint a new token for the ERC or just transfer some Ethereum Ether to the user's layer 2 address. And then second, like on the other hand, if you want to withdraw any tokens from the layer 2 to the layer 1, you interact with the layer 2 bridge contract called like to withdraw the tokens. And then the layer 2 contract bridge contract basically will also emit an event that relayer we're going to monitor. But at this time, so relayer does not no longer wait for layer 2 block confirmations. It will wait for this block that including this withdraw transaction to be finalized in the layer 1. At that time, like then it will send out this transaction to the layer 1 bridge contract, which then finally will transfer that token to the user's layer 1 address. Okay, so for our pre-alpha testnet, so we have like Scroll layer 1, so we deploy as a fork of the Ethereum with the proof of authority-based consensus, and then Scroll layer 2, which is a zero-knowledge rollup, deploy on top of the Scroll layer 1. And right now we are running 5 provers, like a small cluster on the back. And then, so right now as I talked before, like we only have the block proof, so we just mainly like we just roll up every blocks generate a proof for every block and then just route that block proof to the layer 1. We haven't like done finished aggregating multiple block proof into like a single proof. And then we have a few pre-deployed applications on top of the pre-alpha testnet. So we have faucet application on top of the Scroll layer 1. And then second, like we have a bridge contract on both layer 1 and layer 2 for any relaying for transport tokens between layer 1 and layer 2. And then a swap application that is a fork of the Uniswap v2 that's going to give users like ability to swap tokens and also provide liquidity on the layer 2s. And then we also have developed a small like a rollup explorer that's going to show the block status, whether it's being pre-committed, committed, or finalized on the layer 2. So you can see like all of the block numbers and then like corresponding block hash and then whether like it's finalized or not. And they're also going to show this transaction hash that's going to, like, for example, the commit transaction hash will correspond to the transaction that's going to roll up the data, and the finalized transaction is going to correspond to the roll up the validity proof to the layer 1. Okay, so before I go into the demo, so there's like also you have like can sign up to become an early testnet contributor. So there's like a sign up at scroll.io, so you can still sign up, and then we're going to allow like allow like a few hundred people to come and test this testnet. And yeah, and then also we're hiring. This like a page for like hiring page. You can find all of the open positions on our website. Okay, so let's do the live demo of that. Let me see. Okay, so so inside like we have the pre-alpha.scroll.io. So if you are included inside the whitelist, you can be access to that. You can go to like a guide, which give you some instructions of how to use the test and how to play with us, step by step. And then so before like when the first time you join the testnet, you will need to go into add all of these configurations to your MetaMask so that you can be able to switch between different Scroll layer 1 and Scroll layer 2. And then we have some example USDC tokens like deploy on the layer 1 both on layer 2. So things like that. So and then the first thing you're going to do is you're going to open this faucet application. Let me see if I'm using, okay. So you can just request one Ethereum and then 100 USDC token on the layer 1s, and it will just show up to like transaction hash, like you're going to issue those tokens from the faucet account. So here we already have like some of the, or I already requested something like that. It will just, it will like show up after like about 15 seconds. I'll just receive a new like the 1 Ethereum and a 100 USDC token. And then that request only, you can only request once, like every 24 hours. If you do that again, I could just show up some error. And then the next thing you can do is trying to, so that token is issued from the, on the Scroll layer 1. So the next thing you need to do is you want to experience the layer 2. So you just should transfer that token you receive on the layer 1 to the layer 2, which you can use this bridge application that I'm going to see. You can see like I want to transfer 2 Ethereum to the, two Ethereum to the Scroll layer 2s, and then click on send. Oh, so I'm not using the correct, yeah. So now I'm on the Scroll layer 1, so you can send the Scroll, the Ether to the layer 2s, and click on send, and then confirm. So we're going to see a pending transactions here, like after a few seconds. And then, okay, so you can now see this transaction has been confirmed, which you can view on the Block Explorer. So yeah, sometimes the Block Explorer just takes a few seconds to show up on the Block Explorer. So and then so you can see now this transaction has been confirmed by 1 block. And after this, you see like that this number goes up to 6 blocks. Then that means like the fund you transfer from layer 1 to layer 2 will be show up on your Scroll layer 2 address account. So I previously transferred 2 Ether tokens that should have not been show up on the layer 2. So currently I only have 1.3 Ether here on the layer 2 account, but probably like after probably 2 to 3 more minutes, and then it will just show up like it will becomes like 3 tokens, 3 Ethers on my layer 2 account. And then so let's see like that. So let's now wait for that time, and then we can go back, and then so we can just play with the like swap. It's also like quite straightforward. You already have some ETH, and you just swap. Oh, sorry, you select a token USDC. So I can swap 1 Ether for the USDC. That would be kind of standard as what you do on the unit swaps. Okay. So now I will just submit that transaction here. I'll probably show another pending transaction here. Okay. I think next thing like you can play with, you can see is the rollup explorer. So there's a few more transactions actually. So people actually are still playing with the testnet. So you can see like there's how many transactions here for the latest blocks. There'll be like a few like the transactions. So you can see the latest 2 transactions probably those 2 blocks like which I was just submitted. So they'll be still at the pre-committed status. And then there'll be like there'll be relayer is going to keep updating, like sending the new transaction, the commit transaction to the layer ones. And after that transaction has been confirmed, then you can see it will be like the commit. It becomes like committed after a while. So probably it's still waiting for the layer 1 to be confirmed those transactions. So this is some transactions already sent it to the layer ones. And then like because we don't have there's a lot of transactions. Okay. Because I think right now we don't have enough provers on the back end. So there are probably like a few, you can see like there's a few blocks has been finalized so that you can see this both finalized transaction hash and then the commit transaction hash. And that will be switched to the finalized status. And then because we don't, right now at the testnet, like we don't have enough proving power, so that we selectively like just prove like 1 in every 2 blocks. That's 1 block will be skipped. Skipped it just mean like we just punt on the generating the ZK proof for that. Yeah. Okay. Yeah, there's probably like one more demo I can show. Like I don't have like time. So we can actually very soon like we're going to support the arbitrary like the contract deployment. So right now we still have only a few pre-deployed contracts, but very soon we'll have like the new functionality support to like to allow you to deploy any contracts you can do. So right now I can show you like some examples. So I'm actually modifying a little bit on the scaffold ease, like which is a great tutorial that by the Austin did like that. So actually I was running this scaffold ease on my own laptop and connect to the Scroll layer 2, so which means you can deploy contracts. So what you can do, like you just do yarn start in the scaffold ease. So I did that some modification in a new branch. So that is connected not to the local node, but to our layer 2 node. So now you can see on the, it will just initialize a website, which you can deploy, debug things. And then, so I previously tried that. So you can call like the yarn deploy. So currently like just the original example have inside the scaffold ease, which have like a very simple example contract you can interact with. So now you can call yarn deploy. Okay, so you first compile the contract you have inside the things, and then it's deploying the smart contract, and then waiting for the contract has been confirmed. Okay, now it's deployed. So if we copy this transaction hash and open inside the layer 2 scans.scroll.io, and then you can search for that transaction. It'll probably take a few seconds to, actually this box scout usually takes, it has some delay to show up the latest transactions. So, okay, yeah, see, this is the latest contract creation I just deployed on the Scroll layer 2, which is like already success. And then if you go back to this, and then so you can see this new contract has been deployed on the layer 2s. And then which you can also interact with this contract you just deployed on the Scroll layer 2, which you can say I can support like the, Scroll layer 2. Okay, now I can just call Shen. And I'll just interact with the, see like I'm connected to the Scroll layer 2 now, just sending this transaction through my MetaMask. And I click on confirm. So I just say like this transaction has been sent. And then let's just refresh. Yeah, so you can see like this transaction has been already updated this purpose like the string inside the smart contract. And then later up, like probably show up like after the prover catching up on this, like you can then see those blocks will be finalized and then generate some ZK proof too around like all of these blocks we just generated. Okay, with that, that's like all of the demo I have. And then thank you very much. if you have any questions, like actually feel free to ask. I can like have probably 1 to 2 questions if you have.
A question.
Yeah.
Have you tested the case where verification fails and you need to roll back?
Usually, I think like that means like there's some bug inside the zkEVM circuit. So if like
like someone just made a your block producer did something malicious or something.
Oh.
Yeah.
Yeah. So I think like right now we are still operating under the assumption like we have like a centralized sequencers. That means like we are not malicious ourselves. But I think in the future, like if something like has been malicious, then I think like we are going to have like this proof generation part will be working inside the prover, so that prover doesn't need to trust the trace are generated by the sequencers. So that you just need to operate on the transaction data like people send out, and then you generate the trace by the prover itself, so that if the sequence is correct, then you should be able to generate like a valid validity proof for that. That makes sense? Okay. Yeah.
Is there an economic incentive system for participating in the reward network?
That like we still like working on some more details, so just like we just like keep updating on that. So I haven't finalized all of the details of the incentives. Yeah. Oh.
So for the bridging, I guess from L1 to L2, you just have a trusted relayer that and then from L2 to L1, have you set it up so that you have to do like a Merkle proof to withdraw from?
Yeah, there will be some Merkle proof associated with the layer 2 exit.
Do you have a plan for what you're going to do from layer 1 to layer 2?
Yeah, I think we also probably do that. Like once you have the decentralized sequencers, you probably cannot trust anything like that. So you should have some proof from layer 1 to layer 2 deposit. Yeah, it could be like a little bit tricky because you need to have some data, like you think like some proof like the state from the layer 1 to layer 2. But I think I was just considering like the research about that.
Does Scroll have plan to do the recursive solution?
Yeah, the aggregation is kind of like one way people call it for the recursive. So basically, recursive is basically you verify your proof inside the circuit. Yeah, but just people have kind of different naming for that.
Do rollers process single transactions or batches?
Batches actually. So right now we processing at the block level like this. So each block you can have a block could have multiple transactions.
So the coordinator selects like a set of block or a set of transactions.
Sorry, what?
The coordinator selects a set of transactions.
The coordinator will just basically receiving the new execution trace from the sequencer. So once the sequencer generates a new block, it will also generate some execution trace, and it will just send to the coordinator.
Could you explain the L2 to L1 bridging a bit more?
L2.
L2 to L1 bridging.
Oh, L2 to L1 bridging. Okay, yeah. I can switch back a little bit. So the L2 to L1 is like someone just send a transaction to the L2 bridge contract, and that bridge contract will just emit an event, and then also like it will send like some proof like associated with that transactions, and then the relayer basically already received this event from the blocks contract, the bridge contract, and then we'll wait for like it will know like which the withdraw transaction will be show up in which block, and we're waiting until that block has been finalized on the layer 1s. And then you will send all of the withdrawal transaction, like withdrawal messages to the layer 1 bridge contract along with some of the proof associated with each withdrawals. And then the layer 1 bridge contract will verify the proof with all of the withdrawals. And then you'll actually for all of if there are multiple withdrawals within the single block, it will just call multiple transactions to transfer funds from the bridges to user's account. Yes, yeah. So I think like that would have a better user experience, but we need to estimate some fees when you call the withdrawals. Estimate like how much fee will associate on the layer 1s to do the transfer.
Is the commit frequency from L2 to L1 determined by time or by amount of transactions?
Sorry, L2 to L1?
The commit frequency from L2, like committing the state back to L1.
The frequency, no, it's just like the waiting, like once like the block has been confirmed for that contain, if a block in the layer 2 block contains like withdrawal transactions, you'll wait until that block has been finalized on the layer 1s, so that the relay can send out all of the withdrawal events inside that block to the layer 1.
Is the block size in layer 2 as same as the block size in layer 1?
That's a good question. So actually, the layer 2 blocks, the limit is not on the gas. Yeah. It's usually limited by the circuit size, how many transactions or how many steps you can include in the circuit. So if you have a larger circuit, that means like you have higher gas limit. But if like smaller circuit, then you have like smaller gas limit you can process on the inside the block.
So since your limit is given by the size of the circuit, your pricing of gas and fees in L2 is a little bit different, right? It's determined differently than for L1.
Yeah, that's also another great question. So yeah, there will be something like so we probably still take like the most of the gas model from the experience, but with some minor tweak. For example, some certain simple opcode that could be resulting in a great overhead inside the circuits, we'll probably tune up a little bit on the gas cost for that opcode. But usually, I think like that, the existing gas cost model is pretty good, like enough for most of the operations you have.
And a follow-up, have you done any analysis of what repricing of these opcodes could mean from the security perspective? Because that's not pretty straightforward, right?
Yes, yeah, so it's like still kind of like inside the research. We have some initial analysis, for example, some of the like the SHA-3 catch-up opcode could be like a little bit cheaper, like in perspective of the ZK proofs. And then there'll be, for example, some external code size of code hash could be like a little bit cheaper. So you need processing all of the contract code you have and then do some hashing on top of that. So yeah, but I haven't like the kind of fully, like there definitely will be some security concern. We'll just also need to think about all of those different aspects. Okay, so I think I'll just end up now because we're already a little over time. We can have like a 10-minute break and then we can come back to the second session where Ying Tong is going to talk about Halo 2 and then Mason is going to talk about zkEVM architecture. All right, thank you everyone. programming the Halo 2. And the Halo 2 is kind of like a framework or anything to use to build the zkEVM. So let's welcome him.
Thank you. So yeah, as Haichen said, Halo 2 is a proof system, and Scroll's zkEVM is built on top of Halo 2. So this talk will give you a high-level intuition for how Halo 2 works, as well as some actual examples of how the API looks and some things you can do with the API. And then Mason's going to come and show you like what the Scroll team has actually done on top of this API. So Halo 2 proof system can be split into 3 parts conceptually. The front end is arithmetization, and this is really, as a circuit writer, what you'll interact with the most. So this is where you turn some program and some satisfying witness into a polynomial representation. And often, there are different ways to arithmetize some relation. And the one that Halo 2 uses is called Plonk, or Plonkish arithmetization. So after we've gotten a low-degree polynomial that represents our circuit and witness, what we do is commit to it using a polynomial commitment scheme. And so this is the part you'll interact with less. But I think what's interesting to note here is that this part is also quite modular, and it's quite easy to swap out a polynomial commitment scheme, but keep the front-end arithmetization. So in fact, what Scroll has done is they've swapped out Halo 2's inner product argument, and they've replaced it with something called KZG commitments. And the reason they've done this is that KZG proof is easier to verify on Ethereum. Ethereum has a precompile for pairings on the BN256 curve, so it's very cheap to verify a KZG proof on Ethereum. And the last component of Halo 2 has actually not been implemented yet. This is the accumulation scheme that enables proof recursion and proof composition. So I think you saw a preview of that with Haichen's aggregation circuit. It's pretty much the same idea. It's when you can make a statement about not just one circuit, but many circuits, or like a trace of execution across many circuits. Also interrupt me at any time if you have questions. Okay. So in today's talk, I'll focus more on the front end. I think that would be the most useful and interesting for you. So a history of what I call Plonkish arithmetization. It originated with a paper in 2019 by Aztec. And basically, it introduced a very flexible proof writing framework that allowed the use of custom constraints as well as things like lookup tables. So these were extensions on top of the original Plonk paper. And a few of these, actually, yeah, custom constraints and lookup tables are essential for a complex circuit like the zkEVM. So being able to define highly expressive relations and capture the state transition rules of the EVM is very important. And being able to look up results across circuits is also important in composing circuits. So you'll see more of this later. So to go quickly through Plonkish arithmetization, the original Plonk paper defined this, what I call vanilla Plonk. They defined this single constraint that includes some linear combination of variables. So by toggling the values of the variables in red, so these are the selectors, we can express either an addition gate or a multiplication gate. So for example, an addition gate is when you set QL and QR to 1, QO, the output, to -1, and then QM to 0. And you see that the result of that is you're saying xa plus xb minus xc equals 0, right? So you're saying a plus b equals c. And if you set these queues to a slightly different configuration, you can have a multiplication gate. So over here, what we get is minus xc plus xaxb equals 0, right? So a times b equals c. Yeah. So this was the vanilla Planck, and really it was already quite powerful. With addition and multiplication, you can basically express anything. Now, and a further improvement over vanilla Planck was called turbo Planck. And turbo Planck actually introduced custom gates. So instead of being stuck with one default constraint, you're now free to define your own gates in whatever linear combination you want. So I can define an addition gate, I can define a multiplication gate, and I can even define a Boolean gate that's just saying like a squared minus a equals 0, right? And all you have to do at the end of your protocol is to combine these gates using some random linear combinations. So for example, some power of a random verifier challenge to keep these gates linearly independent. Cool. So those are custom gates. Another sort of superpower of the Planckish arithmetization is permutation. So this is also what people refer to as routing the circuit together. Essentially, it's a way to enforce equality between two wire values, right? And this is a global sort of constraint. And you can think of it as after having defined all of your constraints, maybe you want to enforce that the output of one is the input to another. So you could wire them together with an equality constraint or a permutation. And at the end of the whole circuit, this permutation is checked globally. So let's see. So like intuitively, you would just have one polynomial with your actual value assignments and one polynomial that's permuted, and show that the permuted polynomial evaluates to the same value as the original polynomial. Yeah. Questions? Okay. Right now I'm just kind of speeding through the toolbox that Planckish arithmetization provides us, and we'll see some fun use cases later on. So the last, and I think probably the most heavily used superpower is the lookup. So really the lookup is, well, let me take you through a use case first. So the lookup becomes interesting when we're trying to perform some snark unfriendly operations within the circuit. So anything that's like operating on bits or anything nonlinear is usually very expensive to express in terms of linear combinations, right? So instead of trying to compute, say, SHA in the circuit, we could just pre-compute outside the circuit the hashes of some predefined set of pre-images. And what we could then do is load the pre-images and the hashes into a lookup table in the circuit. And so now whenever we claim to have performed a successful SHA in the circuit, we would just need to prove that it's some subset, that it appears somewhere in the list of legal pre-image hash pairs. Yeah. So this is the use case for lookups. Another way you can think of lookups is as a sort of looser permutation argument, where you're not like specifying the the individual position of each permuted value, but rather you're just saying that these values have to appear somewhere in the original values. So it's a subset argument. Yeah. So I think Mason's gonna go into this, but one-way lookups are used in the zkEVM is to communicate between their state circuit, which keeps track of reads and writes, and the EVM circuit, which uses the results of these reads and writes in opcodes. Right, so basically the idea here is that to check the legality of reads and writes, it's more useful to order them in a certain way, whereas to actually use them in opcodes, it makes more sense to order by opcodes. So we depend on the state circuit to produce a lookup table called read-write containing all legal reads and writes. And then the EVM circuit can then use this table as a random access to basically get the values that it's using when executing opcodes. And yeah, that's all I just explained. And in fact, this cross-circuit lookup, it appears not just between the state circuit and EVM circuit, but between a whole bunch of sub-circuits linking the zkEVM mega circuit together. Yeah. Okay. So that was the high-level overview. How am I doing on time? YOLO. 15 minutes? Okay. That was the high-level overview. So hopefully you got a sense of what you can do with Plonk. You can define custom constraints. You can define global permutations between values. And you can define lookup tables that allow you, basically give you a shortcut and allow you to avoid doing expensive operations in circuit. So now I'll go more into the Halo 2 implementation of Plonkish arithmetization. And this will help you understand Mason stuff later. Yeah. So the mental model of a circuit in Halo 2 is a matrix with m columns and n rows. Now each cell of the matrix contains a field element from some finite field f. And mathematically, what are these columns and rows mathematically? So each column corresponds to some polynomial pjx. So the columns, let's index the columns by j. So pjx is a Lagrange interpolation polynomial. So in other words, it's a polynomial expressed in the Lagrange basis. And pjx has this quality that when evaluated on omega I is the row number, it gives you the actual value that you witnessed there, xij in that cell. And omegas here are the nth primitive root of unity in the field. What this means is that omega raised to the power of n is the identity element. Yeah. So maybe it's not super important. Yeah, I've never. Yeah, to write a circuit, you maybe don't need to know this, but I would like for you to know this so it doesn't seem so magical. Like concretely, these are the mathematical objects behind the rows and columns. Okay, but if you don't care about this, we can actually proceed just thinking of them as rows and columns. And what's important for you to know is that there are different types of columns. So the first type is called, was what we call instance columns, and you can think of them as public inputs if you're familiar with R1CS. So these columns contain public values, meaning that they're known both to the prover and the verifier, right? Whereas there's a second class of columns we call advised columns, or you can think of them as witness columns. So these contain the prover's witness, and this is absolutely secret and not known to the verifier. And the final class of columns actually define the circuit. So these are the fixed columns, and these are baked into the silicon, basically. And these define the custom constraints in the circuit. These define constant values. These define your lookup tables in some cases. And so this is known publicly as well to the prover and verifier, and in fact, it's encoded in the proving and verification keys. this defines the relation that your circuit is expressing. Yeah. Questions? Yep.
Why did you say baked in the silicon?
Oh, so the question is why did I say baked in the silicon? So I was just trying to be cute and draw an analogy to the silicon when we're making chips, and I was trying to make the point that these fixed columns are your circuit definition, and so from one proof instance to another, the fixed values cannot change. Yeah, because once they change, you're proving a different statement. So, yeah. Whereas from one proof instance to another, your instance and advice values can change. Yeah. Any other questions? Okay, cool. So now we can go into a very simple example of how we would use this mental model to express a circuit that constrains the inputs to the Fibonacci sequence. So to do this, what I'm gonna do is define a custom gate. So the custom gate here is, let me exit here. The custom gate is this part. So I'm saying that A0 plus A1 minus A2 equals 0. Or in other words, I'm saying A0 plus A1 equals A2, right? So now there's a QFib selector that's toggling the custom gate on or off. And the effect of QFib is if it's set to 1, then A0, A1, and A2 had better fulfill this relation for this whole thing on the left to evaluate to 0. But if QFib is set to 0, then this expression evaluates to 0. And that's equivalent to you saying that you don't care, you don't want to check this relation on that particular row where QFib is 0. So for example, you're doing some other things in your circuit, and on that row, you don't expect the values to be from the Fibonacci sequence. You would set QFib to 0. And this is the power of custom gates, that you can create these like self-contained blocks of logic in your circuit and have a very expressive circuit that makes use of a bunch of different regions. And I will also set over here A0 plus A1 equals A0 on the next row. So what I'm trying to illustrate here is that in defining your custom gates, you do have access to cells on different rows. Yeah. So the Planck, because it's defined over the roots of unity, it allows you to rotate through the domain and access values on different rows in the circuit. And then I've done the same thing, but moved it one column over. So, and in addition, I could enforce a permutation from the output of one row to the input of the next row. Yeah, this is probably not the best way or not the only way to implement the Fibonacci circuit. So here, you see, I can also enforce that the Fibonacci circuit starts at 1 and ends at 13. And I can do that by demanding equality between my public input and some elements of the witness. Yeah. How am I doing on time? Like 1 minute, stop? What? Oh, I can, 10 more minutes? Okay, cool. Nice. So that's a toy circuit that makes use of a bunch of tools in the Planckish arithmetization. Any questions? Yes?
Is the first column always used just for like initialization like this?
Oh, so the question was, is the first column always used for initialization? So that's a very good question. In short, no. So it is a degree of freedom provided to the circuit designer of how many columns of which types they want to use. So this is the circuit configuration, and it's set up by the circuit writer. And yeah, I said it's a degree of freedom because it's also a lever for optimization. Heuristically, more columns would produce a larger proof because each column requires a commitment to the values in that column. However, heuristically, let's say our circuit has some complexity measured in area, and like we preserving the area, we chose a configuration with more columns and fewer rows. So fewer rows would mean a faster prover because it would mean a smaller FFT. If you go below the next power of 2, you would halve the size of your FFT. So yeah, in short, the number of columns and types of columns, these are degrees of freedom, and they can be used to optimize your circuit for whatever setting you're interested in. So if you want a fast prover, you would have a wide and short circuit. And if you want a fast verifier, you would go for a narrow and long circuit. Yeah. Jordy?
Does this, so this way of designing, does Halo 2 do it automatically, or you have to design, so you have to take into account when you are designing that?
Yeah, so the question was these optimizations or these choices about number of columns, number of rows, are they made automatically by the Halo 2 backend, or do you, the circuit writer, have to do it? So the answer is you have to do it currently. But the Halo 2 backend helps you out to an extent. So this is a good segue to the next slide. Basically, the Halo 2 backend helps you to pack your circuit vertically. Yeah, so right now we have a helper called the layouter that does 2 passes of your circuit. So in the first pass, it measures all the regions in which you've made assignments. And in the second pass, it compacts the regions whenever there's free space available. And over here, this is a real circuit. So this circuit is ZCash's Orchard circuit. So Orchard is the latest payment protocol in ZCash. And the layouter helped us to get from like almost 2 to the 12 to below 2 to the 11. So that's double it made our prover twice as fast. Yeah. But I think a lot of manual work is still involved right now in deciding the configuration, and some experience is required. And we are interested in writing tools to automate this. So like a tool that I would like is you, the circuit writer, tell me what you're optimizing for, like fast prover or fast verifier. And then you tell me some bounds which I cannot cross. And then all the rest should be done for you. Yeah. Any more questions? Yes.
So when like you're designing custom gates, you know, you can do this like relative references across rows, right?
Yeah.
It seems like this makes it harder to do optimization.
Oh yeah.
What's the trade-off between using more copy constraints and using like local references within?
Yeah, that's a great question. Someone just asked, so when you're designing custom gates, you can make relative references to other rows. However, this makes the circuit harder to optimize. So what is the trade-off between using these relative references versus not using them? So basically, how Halo 2 deals with this trade-off is with an abstraction boundary called regions. So a region is defined by a common relative offset. So all cells in the region share the same relative 0, right? And so within a region, what you should do is you should define all you should define all custom gates that depend on having some cell available at some relative offset. Okay, but let's say this gate, let's say the cell on the next row was in a different region. Then basically Halo 2 does not guarantee that the constraint will hold. And the reason here is that Halo 2 considers each region as a self-contained block of logic. And after a region is defined, the layouter has complete freedom to move them around like Tetris pieces. Yeah, so if you define a custom gate that uses some cell in another region, then after one layouter pass, that region might have moved somewhere else. And yeah, it's your fault. Yeah, so basically when making relative offsets, do it in this, when referring to relative offsets, do it in the same region. Yeah, that's a good question. Any other questions? Okay. I think I am done-ish. Here are some other gadgets we've written in Halo 2. So the Poseidon hash, we made a hash function called Sinsemia. That's kind of like a Pedersen hash. This is elliptic curve cryptography, and that's SHA-256. Yeah. So I am done. The other slides, the remaining slides they concern Halo 2's current state of development, as well as some open problems or some things in our wish list and in our roadmap. You can talk to me about it afterwards, or you can join our ecosystem Discord to continue the conversation. Yeah. Thank you. Any questions? Yes. Oh, that's a good question. Someone asked, between powers of 2 in the FFT, do we see step changes in performance, or in short, yes. Yes, we do. So once you cross, let's say, 2 to the 11, you're at 2 to the 11 plus 1, then you need to do a 2 to the 12 FFT. Yeah, so you might as well.
So 2 to the 11 plus 1 is equivalent in increments to 2 to the 12?
Yes, exactly. Yeah. Jordy?
Regarding the recursion part,
Yeah.
you mentioned that was not ready. Can you give us a little bit roadmap or
Yeah.
status?
So Jordy asked us about the recursion roadmap. I have this super cool thing. Let me see. What is it? Developers? Halo 2 Focus. So this is an internal tool that the ZCash team uses to map out our sprints. So this is the recursion specific part of the deck. And I'm trying to find the critical path. So these 3 nodes are like the critical path for implementing recursion. Okay, is the deck, I'm surprised not every team uses this. This has changed our lives. Yeah, so there's some parts that we've already implemented, like parts to do with communicating public inputs from one curve in a cycle to the other curve. But there are parts that can be implemented in parallel and that we're working on. So in fact, let me see, on the roadmap, yeah, like we have plans with Filecoin to, apply Halo 2 recursion to the Filecoin, like proofs of space-time and proofs of replication, so that those proofs don't take up too much space on the Filecoin chain. And we're also talking with Ethereum about using Halo 2 for the recursive snark for their VDF. Although I think they've also implemented this in Nova. Yeah. So Jordi, this is our roadmap. Yeah. Yeah. Any other questions? Yeah.
So in the Fibonacci example, you use a selected polynomial to state where the constraint needs to apply. In the star characterization Fibonacci example, they use a vanishing polynomial instead. So what's the trade-off in terms of performance, proof, and verifier? Using sparse vanishing polynomials versus fixed selector polynomials?
Yeah, that's a good question. So Remco asked, in this Fibonacci example, we're using a sparse selector polynomial to sort of toggle the constraints on and off, whereas the Starkware people use a sparse vanishing polynomial instead. And what are the performance trade-offs? I actually don't know. I would need to learn more about their approach first. Yeah. Unless you have some idea. Okay. Cool. Other questions? Okay, thank you.
Okay, yeah. Hello everyone, I'm Mason and I'm going to talk about Scroll and the zkEVM that we're building. So there's just so that we're like clear on like what we're building, there are a couple of different types of like zkEVMs. And so the sort of like the top one is like language level. So this means that you take like a higher level language like Solidity or Yule, and you transpile that to a snark-friendly VM, and then that's sort of like what you produce a zero-knowledge proof of. And so this is what Matter Labs and Starkware are doing. And then there's bytecode level zkEVMs, which is what us, Scroll, Hermes, and Consensus are doing. And so in these, you interpret the EVM bytecode directly, and then you can prove. You sort of prove the the bytecodes are executed correctly, like one by one. And so I guess like in our case, like we have like one gadget that proves each, or usually like one gadget that proves each EVM opcode. And then in Hermes' case, they I believe have like micro opcodes, and a bunch of these micro opcodes will map to each EVM opcode. And then but there are still certain differences between this and like what happens at like a consensus level zkEVM, one of which is like we use like a different state like hash function, so the state roots are different. And then potentially like we discussed earlier, like the gas pricing might be different. And then then the final one is a consensus level zkEVMs, and so this one would basically just be a zkEVM a zk proof that in fact that sort of like the state root transition is correct according to like the Ethereum L1 consensus. And so this is what, like on the roadmap for Ethereum, what is meant by the zk snark everything node. So yeah, we're building a bytecode level EVM, zkEVM. All right, so let's talk about like what we're actually doing. And so Haichen had a diagram that was sort of like that showed the like our workflow, and just to go over it again. So like people have like transactions. We run them on our forked geth node, and this produces an execution trace. So there's the execution logs, block headers, the transactions themselves, the bytecode for all the contracts that got created, used, and then Merkle proofs for all the storage slots that got touched. And then this gets fed into our zkEVM circuit, like all the circuits that comprise our zkEVM. Those circuits produce a bunch of proofs. All these proofs are then fed to the aggregation circuit. The aggregation circuit produces a proof that all these proofs are in fact valid, and this like aggregation proof gets sent to the L1 contract, which does all the stuff that Haichen talked about earlier. And then at the same time, the geth node provides some data to the L1 contract, so that everyone else can figure out like what it is the validity proof is a proof of. Okay, so so in my talk, I'm just going to be talking about the stuff that goes into the zkEVM circuits, and then the stuff that comes out of it. So the execution traces, and then the proofs. Okay, so at like the very at the very top of our zkEVM is the EVM circuit, and so this constrains the operation of like the EVM state machine. So what happens here is there's things like the amount of gas that you have left in your execution, the like program counter, various call context, block context, constraint variables. Let's see what else is there. So it's sort of just like a lot of the bookkeeping that you do as the EVM sort of like goes like bytecode by level, opcode by opcode, like executing like the transaction and calls, and so, but then to keep like the engineers like I'm one of the engineers at Scroll, and so like to keep us sane, we like break this down into a bunch of other components. And so like the first one is there's a bunch of like ZK unfriendly opcodes, like catch-check is one, and then like all the like logical operations like and or, exclusive or, not, what have you. And so these are done by lookups. I mean everything else is done by lookups too, but these are also done by lookups. And so like in the case of the like logical like and ors or whatever, these are done by like the lookups that Ying just described into fixed tables. So rather than like write the constraints that show that like, hey, like A and B is equal to C, we just look it up directly. There's a table that has like every single input to the and then the corresponding output, and then because these are fixed, like everyone can just see that in fact like we have filled out this fixed table correctly. And so okay, so yeah, like I'll talk about how that's actually possible later, because like and then so catch-check has a it has like the table that Ying just described earlier, right, where there's a table that has like all the pre-images in it along with the catch-check values in it. Okay, and then there's also the so I guess like in Ying talk, she called it the state circuit, which is actually what it's called in the code, but I think it's more clear to call it the RAM table. And so this verifies that like the reads and writes aren't actually like that the reads and writes are like have been done like according to like how you think they would be done, right? Which is so that like if I write a value to some slot and then I read the like a value from it later, that the value hasn't actually changed. And then let's see. So then there's a bunch of other lookups. So like there's the bytecode lookup, right, which basically proves that in fact the opcodes that the EVM claims it's executing are in fact the opcodes in the contract itself. There's the transaction lookups, which verify that the like the call data in the transaction is the call data and the transactions that we're claiming, and then the block context, which is sort of like has things like the block number, block hash, timestamp, stuff like that. So all these are done by lookups, right? And so this sort of just like it's like how our circuits like sort of talk to each other, and then so there's more circuits on top of all of these that can make sure that the values in these tables are actually correct. So for the and or like the logical operation table, right? These are fixed, so we don't need a circuit to prove that these are correct. For the RAM circuit, for the RAM table, like we have a circuit that shows that in fact the values aren't changing in between reads and writes. And then there's also the MPT circuit, which is showing that for initial reads, that the values that we're initially reading out of, say, storage slots are can actually be found in the state tree. And so there's like various things like the bytecode circuit, and there's like interdependencies between all of these, right? The bytecode circuit actually has to look up catch-ack values. The catch-ack circuit proves that every row in the catch-ack table actually does correspond to the SHA-3. The TX circuit has to look up into the catch-ack circuit table because, right, you have to verify that in fact these transaction hashes are correct. And then additionally, you also have to verify that we have signatures for all of these transactions, because so we can't just like sort of like stuff it full of transactions that we're making up. And then the transaction signatures are themselves verified by the ECDSA circuit. So this is sort of how everything depends on each other in the zkEVM circuit. So yeah, if you guys have any questions, feel free to ask. All right.
Oh, yeah, quick question.
Yeah.
So I might not have full context, but the verifier will have access to all of the like raw numbers to look table. Is that right?
No. So well, so I guess like right. So there's the aggregation circuit at the very end, right? So the verifier has like actually access to basically none of these tables other than the and or this one, right? Because this one is fixed. The other ones are assigned. Well, actually, sorry, that's not true. I think some of them are like instance columns, like what Ying was saying. So these are public to the prover and verifier. And then so this table is fixed. But then, for example, like the RAM circuit is an advice. These are all advice columns, so the verifier doesn't actually see them. The verifier only gets like a proof that the prover provides that like all the constraints in these different circuits are satisfied.
So would there be like some Merkle type constraints that like to make sure that the bytecode that you're claiming lives here actually is,
Yes, I believe there should be some more like there should be some more like dotted lines here. I think, yeah, right. For example, like yes, like the you need like an MPT lookup to confirm that like these bytecodes that we're claiming are like actually in the state tree.
Like the MPT circuit, I guess, would talk to the.
Yeah, so I think there should be like an MPT table here that consists of sort of like MPT proofs for like sort of all sorts of facts, and then the bytecode circuit would look up into it to every time it's like saying like, hey, this is the bytecode at this address. Okay. So I guess, yeah, so that's sort of like the high level picture. And then now I'm just going to talk about like sort of like how some of these circuits work. So the EVM circuit, the one at the very top here, is sort of basically looks like we have like one region for every like execution step, I guess. And usually each execution step corresponds to an opcode. And so like in this example, you can imagine like that the opcodes that we are interested in proving can like the first one's push, and then I add whatever is on the stack, and then I multiply, and so on and so on. And so to talk about slot I in particular, right? So there are so all these. So I guess so A1 through AW are sort of all advice columns that the prover assigns, and then QOP basically is a selector column that just says basically it's one every like however many block. Like I think in this case, right, it's every 6 rows is one, right? Which just means that basically every 6 rows I prove the execution of one opcode. And so there's some context variables. So PC stands for program counter, SP is the stack pointer, gas is how much gas is left, and then there's more. And then there's also these sort of selectors for each of the opcodes themselves. So there's one for addition, one for multiplication, one for shift right, and so on and so on. And there's also error states of the VM EVM, right? It's I'm out of gas, I've overflowed the stack, whatever. And then there's these V0 through Vn are sort of operating values, and so these have basically context dependent values, I guess context dependent names. So depending on which opcode I'm currently proving, they have different interpretations. And so let's see. Okay, so I guess, but first, one thing that we should talk about is how do you handle 256-bit words? So the EVM has 256-bit words, which is unfortunate because the field prime that we use is slightly smaller than 256 bits. And so the way we deal with this is, let's say we have a word A, and then we break A down into its constituent bytes. So there's 32 of them. So right, so A is equal actually equal to this value here, right? So the least significant byte plus 256 times the second least significant byte, and so on and so on. And then what we do is actually when we want to assert the equality of two EVM words, rather than check that if we have A and B, right, rather than check that A is equal to B, we can't do that directly. So instead we compute this random linear combination of them. And so this is sort of like the random linear combinations that Ying Tong mentioned earlier between custom gates, where so you generate this theta according to some public randomness, and then we compute this sum A sub RLC, which is instead of using A0 times A1 times 256, you just have A1 times theta, and so on and so on. And then this thing mod FP will actually be small enough to fit in the finite field. And so this just means that when we compute our lookups, we just compute the RLC of these values instead of just using the bare values. And so this technique of breaking up the words into bytes also comes up when we're computing things like logical operations on the words, right? So if you want to compute A and the bitwise AND of A and B, then we just compute you can just do this byte by byte and look up the bitwise AND of A0 and B0 and A1 and B1 and so on and so on. So okay, so let's say we are back to the add opcode. So we also have these opcode selectors, and so the constraints for these selectors are basically what they're supposed to be is 0 and 1 binary selectors, and exactly one of them is 1, and the one that's 1 is the opcode that we are trying to prove. And so the constraints that we have in this case are so it's basically the selector times 1 minus selector is 0, which means that each selector is either 0 or 1, and then the sum of them is 1, which means that exactly one of them has to be 1. So this sum here can't overflow because there's not enough terms in this. There's not enough terms in this sum to overflow. And then, so in the case of addition, right, we we prove it byte by byte in the way that you do addition, like with like in base 10 on a whiteboard, right? So this first constraint, right, says that the first byte plus the second byte of the first byte of A plus the first byte of B is equal to the first byte of C plus potentially the carry bit times 256. And then this thing, so this thing gets repeated for all 32 bytes, and then we are missing constraints here that say that in fact the carry bits are 0 or 1. And then, right, but then if all these constraints hold, then the claim will, like, then it will hold that, right, the value represented by the bytes of C is actually equal to like A plus B. Okay, and then, so then there's sort of like EVM bookkeeping to do, right? So, right, the program counter here has advanced by 1 because now we've successfully proven the addition opcode. The stack pointer has gone down by 1 because the addition opcode pops 2 values off the stack and then pushes their sum onto it. And then the then the gas has gone down by 3. All right, because that's the gas cost of the addition opcode. And then there's also more, right? Like we have to check that the stack pointer is still less than 1020, still less than 1024, and things like that. Any questions so far? Or, oh yeah.
Yeah, I had a question about the random linear combination.
Yeah.
Stuff. And so, is there some way to? I guess where does the randomness come from? Do you need to do an extra step in the trusted setup to get like?
So I think the randomness would be like basically some hash of like the public inputs that you pick. But yeah, like you have to be careful about it,
Yeah,
because if like.
Like a hash of the like transcript so far or something.
Yeah, yeah, right. But yeah, like you can't just insert any value for theta in there. And then there's like a lot of like carefulness you have to do, right? You have to actually make sure that none of the values that you're randomly like combining are like themselves random linear combinations, because then there like issues come up there too. Sorry, you also had a question, or?
Yeah, I was like maybe a naive question, but
no, it's fine.
like what's preventing you from picking a bigger prime and avoiding like having to do this random linear combination?
Sorry.
So you said the reason you have to do
Yeah.
this random linear
Oh,
combination,
yes,
right,
yes.
is the prime is just
Right. So if the prime were larger than 2 to the 256, then this is like actually like a hardware problem for us, right? Because we have to you have to multiply these larger primes. Now they don't fit into 256 bits. So now like yeah. Okay, let's see. Okay, so and then okay, so now we like in our EVM circuit we have like C, which is equal to A plus B, but then all this sort of needs to be like communicated with like the RAM is communicated with the RAM table. And basically what happens here is that, right, like when we pop the A from the stack, what actually happens is that the EVM circuit says like this lookup, this row exists in the RAM table, and then so I think this value corresponds to VB, right? So I'm saying that at position 1023 I got VA, at position 1022 I got VB, and then this push goes back to position 1022. And then so the EVM circuit, all it's really doing in this case, right, is constraining that VC is equal to VA plus VB. So which brings me to the RAM table, or actually, no, it doesn't. Okay, so then we so far I've all just been talking about the constraints themselves. So the other part of generating the proof is you have to fill in the witness. You have to actually fill in the witness from the geth traces that we have. And so this is, I mean, there's just like a lot of like sort of like data processing to do here, right? Where like the geth traces come to us in like a JSON form, and then we have to process them so that now there are these like Rust structs, and we fill in the context, right? So like geth I believe just tells us like here's a program counter, here's a stack pointer, here's the gas, right? But then some like these things, right, don't have a corresponding geth value, so we just have to like compute them ourselves, right? But this is just like, okay, like put one where for the opcode that we're executing right now, and then 0 for everything else. And then, right, so then we also have to fill in like the intermediate values that were used to prove that in fact VA plus VB equals VC. So like here are all the bytes of VA, here are all the bytes of VC, here are all the carry bits, and here are all the bytes of VC. Okay, so yeah, so I think like, yeah, Halo 2, like in the main branch right now only lets you look up from fixed tables, but we have we've like modified it so that you can now look up, the lookup argument actually works for like into advice columns as well. And so this is very important for us because, right, like a lot of our lookups are not fixed, right? Like the RAM table changes every time for every new transaction. So it doesn't, yeah, so it wouldn't work if they had to be fixed. And so the RAM circuit is the thing that constrains the RAM table. And so, right, so earlier when we're executing the VM or the EVM, you sort of like these are random access, right? So you might read from the stack, and then you read from the memory, then you write to the stack, and then you read from the storage, and then so on and so on, right? And so, but what we need to prove is that like if I write to the stack and then I read from the stack, then that value doesn't change in between. And so, but like the order of the reads and writes in the EVM circuit aren't conducive to proving this. So the RAM circuit basically has the same contents as the RAM circuit proves this, and the way it proves it is it sorts the reads and writes in a different order. So instead of them being in execution order, in this case, right, it sorts them so that all the stack read writes come first, then all the memories, and then all the storage reads and writes. And then within the stack reads and writes, we sort them additionally by the address and things like the call ID, so that we can verify that within a call ID, we have read-write consistency like for every particular stack address. So let's see. So yeah, so like in this case, right, so this read-write index sort of tells you how the EVM, I guess, yeah, like how the EVM like in what order the EVM accessed these elements. But then in the RAM circuit, right, the RAM circuit constrains that these things appear in this sorted order, and right, and then now like we can basically write these simple constraints that say like if it's a read, then the values don't change, and if it's a write, then the value can be whatever you want it to be. And then additionally, you also have to add constraints, right, saying that, right, for like an initial read to a stack should be 0, an initial read to a memory should also be 0, and an initial read to a storage should be like whatever the MPT circuit says it is, right? And so that's also a constraint that has to show up in the RAM circuit. Yeah?
Did you say that's sorted by address?
Yes.
And what's the reason for that?
Well, because like you want all the reads and writes to a particular address to be like one after another, right? Because, right, it's like what Ying was saying earlier, like you can't, okay, like it's like you don't want to have these like long distance constraints, right? Where like, oh, I'm like, you actually can't even express it in Halo 2. Like you can't say like, oh, like I read it here, right, and then like 10 rows later, or like maybe 100 rows later, depending on like what's happening in the EVM, right? Like I read from it, and then I want these two values have to be the same, right? So if they're sorted, then like it's actually just like the next one.
It's sorted by address, but also it's sorted temporally for each address.
Yeah, so it's the sort order is like the tag, the address, and then the read-write index. This is actually like a simplified version of it. There's like even more things because there's there's other things that are effectively like random access, like different call context variables are in this transaction log, logs, like even things like oh, like here are the like accounts that I've accessed in this transaction, and so all of these are in the RAM circuit, but they're not in the slide for simplicity. Okay, anything else? Okay, so yeah, so these right, so sort of just these are just some of the constraints in the RAM circuit, right? So that if it's a read, then the value has to equal the previous value, i.e. it can't change, and then we also have to check that that these values are valid, right? So RW is 0 or 1. The tag is one of stack, memory, or storage. So like these correspond to like just 1, 2, 3, and that in the case of the stack, right, the address has to be within 1024. And then so yeah, this is like what I was talking about earlier, like this constraining the sort order of the keys, right? So basically, first they're sorted by tag, then they're sorted by address, and then they're sorted by read write index. And there's actually a final constraint that like you can't repeat a read write index either. All right, so yeah, just want to thank all the community members who have helped us write this code. And are continuing to help us write this code. So yeah, are there any questions? Any more questions? Oh, yeah?
Sorry, maybe could you explain a little bit what the advantages are of going for bytecode equivalence rather than the transpiled version?
Well, I guess. Okay, so I guess like one is just like there's some like implementation things that are like easier because you can. I guess like sort of like what kind of advantages are you interested in, or like because like there are trade-offs, of course, right?
Yeah, I was just thinking that since like presumably as far as portability, like people generally have their source code in Solidity or whatever, and so like those should be equally the same. So like are there implementation things that are easier? Are there like nuances that the other version, the transpiled version, doesn't support? Or?
Yeah, I think I'll defer to Haichen.
Okay, yeah. So I think one important implication is like we don't want developers to use another set of the tool chain. So they reuse a lot of things like bringing data into JSON, and you can reuse a lot of things. You don't need to install extra plugins or like another compiler, and also extra compiler like infrastructures could be like adding more security concerns, like if there's anything like you need to trust another compiler that's built by another team. So instead like the whole like Solidity compilers. All of the infrastructure to build upon that would be like probably need some extra modifications into the daily workflow. So that by keeping this bytecode compatibility, so we can maintain the fast developer experience for like all of these things.
Oh yeah, Remco?
Is that also do you also need the bytecode compatibility to implement the create opcode? Like is this something you can uniquely do if you go down this route?
Well, yeah, like I mean, yes, I guess yeah, like in the case of like create, right, like there you would need to. I mean, like yeah, like I think like you could work around that, right? But yeah, like with bytecode compatibility, you don't have to worry about it.
It breaks like the architecture storage.
Anyone else? Wait, what? Oh, okay. All right, cool.
So we'll have another 10 to 15 minutes afterwards, like do one last session for the workshop.
right, so I understand like, you're probably already very tired for like after the whole workshop. So in the last talk, we're going to talk about some performance optimization for the zkEVM. So I think first things that we're going to, I'm going to describe like what's happened inside the Halo 2 provers or inside the Plonkish provers with the KZG commitment. And now then talk about like, what kind of optimization we did and then what's the performance number we have so far achieved. So first of all, like I think previously also Tong showed this kind of diagram of what happens inside this Halo 2 or Plonkish circuit to do. So first of all, at the top level, you have the circuit arithmetization, where you write the circuits. You define all of your custom gates, the lookup arguments, and then the permutation you're going to do to constrain circuits. And then second, like we will convert those circuit arithmetization and then define it becomes into the convert them into the polynomials, and it will becomes the relationship between the polynomials or the constraints between the polynomials. I call it like the polynomial identities. So you can see in this step, in the second step, so we just have the a lot of equations of those all of those polynomials, and those will be the constraints that the prover is trying to constrain and then generate the proof around that. And then last thing, so what you're going to do is using some of the polynomial commitment scheme to do that. And then in our particular case, like you probably need to commit to the your polynomials and then open at a random points that are going to check in the verifier. And what we're using for the polynomial commit scheme is KZG, the commitment scheme. There could be like some other commitment scheme, for example, the IPA used in the original Halo 2, and then there will be Fry as another commitment scheme. But like in our prover we are using for the zkEVM, the Scroll or like PSE zkEVM, is that we are using the KZG commitment scheme. Okay, so actually Ying has already covered a lot about the Plonkish arithmetization. So you have like different types of columns. You have advice columns that's going to put any arbitrary witness data into those advice columns. And you have fixed columns for some fixed data you can put into that. That could be like already pre-processed before you in the verification and approving keys. And then there are selectors that control all of the custom gates and also the lookups you're going to do. And then there's some instant column inside the circuit which is going to hold any public input data inside that. And then there's three major primitives, basic primitives inside the Plonkish arithmetization. So one is the custom gate. So you can define any constraints or relationship between all of different cells with rotations. And you can do the lookup argument with a very powerful thing. So you can prove like a column which had all of the value inside of one column is belong to some of the table columns so you predefine or you can generate use through the device. And then the last thing will be the permutation, which you can copy data from previous rows to the next rows. Those are the primitives you have in the Plonkish arithmetization. Okay, so next we're going to talk about, so by the way, so when we're building the zkEVM circuits, we mainly use the first two, the custom gates, and then the lookup arguments. So the permutation we didn't use a lot inside that because one is the EVM circuit has a lot of flexibility inside that, so the permutation need to be fixed per circuit. That's why like the permutation is not heavily used. So I'm just going to talk about more about the custom gates and lookup argument. So first, the cost of adding a custom gate. So let's take an example. You have this, you define this T-shaped custom gate involve like the 3 elements in the first row and then the 1 more elements in the next row. And you can define this, the constraint is that VA multiply VB multiply VC minus VB equals to 0. And then that will be then translated into this polynomial identity, which you call like A1, which is defined as like the column, like when you commit the column A1, it will become A1x as a polynomial for this column, and then multiply A2 and then multiply A3 minus A2 omega x equal to 0. And here the omega x basically defines like this is the next row with regard to the previous 3 rows. And then because this custom gate may not apply to every rows in these 3 columns, so that's why you have a selector column like and then when you can set a selector to 1 at that rows, so that means like this custom gate only check the row we have like the here marked as 0 in the red regions. And then that's changed like the, that's will be also corresponding change the polynomial identity here, so that you need to multiply one additional polynomial into the previous polynomial we have. So that means like this polynomial will only check whenever the selector is set to 1 at that row. Okay, so then that means like if you in total in your circuit, if you have dg custom gate arguments there, then you will end up into dg number of those polynomial identities in your final proof you need to work on in the prover. Okay, next thing, we'll talk about the cost of adding a lookup tables, a lookup argument, sorry. So for example, let's say we want to prove this, all of the value inside the A1 column will belong into the values into the T1 column, which is some table column there. For example, see like the here you have like the for the A1 you only have value 1, 2, 1, 2, or 1, 2, 3 like that. There has arbitrary values, and you can have duplicate values. And for this table, you only have 1, 2, 3 are all the values you can have for the A1. So what you're going to do, like this could be like there are some different versions of this lookup argument. So I'm talking about the one is specifically used in the Halo 2. What you're going to like in the Halo 2 is that you will generate 2 new columns from the A1 and then T1 into this A1 prime and T1 prime. So you're going to do is like for the A1 column, you're going to sort every value inside A1 column and then create these new columns. And then for the T1, you kind of like sorting this column into like the new things. But what you do is like you will map this value 1 like into the first appearance value 1 inside the A1 column. And then rest of them will just pad with 0. And then you will put like the value 2 at the same row as the first value appear in the value 2 inside the A1 prime column, and then so on and so forth. That's how you generate this A1 prime and T1 prime columns. And the second step is that you need to constrain this A1 prime column is actually using all of the value inside the original A1 column to construct this new A1 prime column, and same for the T1 prime columns. So you need to add this additional multi-set check to constrain the A1 prime and T1 prime from the original A1 and the T1 columns. That means like there's 2 polynomial identities you need to add in your final proof. And then third thing that you see constrain, this is finally the constrain the value that's all of the A1 value will belong into the value inside the T1 prime. So what you're going to do is like you can check all of value inside A1 is either equal to your previous row value, or you're equal to the same value in the T1 prime column. And then you will have some initial condition check, which is like the first value need to be same. That's like how you're adding like 2 more extra polynomial identities inside the proof. So to summarize for the cost of lookup argument, so first like you need to oh yeah, so I forgot to do that. Like when you do this multi-set check, you are going to construct another column like the ZT column, which is like Z column here. I forgot to mention here. So this is going to help you to this kind of helper. So I kind of had way beyond that because there's a lot of math on behind that. But just you create like a new column to check this running sum check. That's going to constrain this permutation check. So that's why in total you will have if you have DT lookup arguments inside your circuit, you will need to add additional 3 DT polynomials or columns you need to construct. So that those kind of are virtual columns which doesn't exist in your original circuit. And then you will have additional 4 DT polynomial identities, those like 4 constraints you have in your final proof. Okay, so now let's take a look at what happens when you generate the proof like in the Halo 2 plus the KZG provers. So first of all, like in the first phase, so we define like there are 4 phases in total. So the first phase is that you are going to assign, like given the input data you have, you need to assign all of the values into your giant 2-dimensional matrix. I would call the witness assignment. And then next things you are going to do is for every column inside your circuit, including all of the advice column, fixed column, like instance columns, etc., and permutations, you are going to commit them. You first need to convert them into polynomials, and then you will do some commitment using whatever commitment scheme you are using inside your provers. So like we call like the commit, like a fx at all of things, those things. And then the second phase is going to do like some extra processing for the lookup arguments, which you need to generate, construct those all of the a prime x, t prime x, and the ztx that's going to use to constrain this lookup arguments. And then for all of the additional polynomials you generated, you also need to generate some commitment. You need to commit all of these extra additional columns there. And in the third phase, what you're going to do is you need to compute the giant quotient polynomials, which you include all of the custom gates constraints, and then all of the lookup arguments constraints, and the permutation arguments there, and then create a giant quotient polynomials, and then with some random linear combination of all of the polynomials you have, identities you have. And then, so that's like the h prime x, which is the hx divided by the xn minus 1, which means that this original hx should hold to be true for all of the value from the 1 to n you have. And then, because this h prime x, the degree of the h prime x is pretty high, depending on like the highest degree you have for all of your custom gates and the lookup arguments. So you are going to slice this h prime x into like the certain number of the slices, and each slice of the polynomial will have the degree up to n like for each degree for each polynomials. And then here, how many slices here is the 2 to the extended k minus k, where this like extended k is kind of the so this difference between the extended k and the k is determined by the highest degree for all of the polynomial identities. So in terms of like what's the degree? For example, here, this L0 times zx minus 1, the degree of this polynomial identity is 2, because you have at most like L0 times z, so that's 2 polynomials multiplied together. So that's kind of the degree called like the degree of all of the polynomial identities. So here the difference is here is the highest is determined by the highest degree of all of the polynomial identities you have. And then you also need to commit all of the slices, sliced hi prime x polynomials here. And then the last thing, what you do is going to do the openings of all of the polynomial you have at the random points and all of the rotations you have. The rotation here is meaning you create like at the current row or the next row or the next second rows, those kind of are the rotations. And then you will use this multi-open protocol at the final to do the pairing check, those kind of things. Running some multi-open protocols. So these are the 4 phases you happened in behind of the provers when you do the proof generation. Any questions so far? No. Okay. So next, I'm going to talk about the different types of computation you happen inside proof generations. So the first is the witness generation, which is just only like in the finite field, you do a lot of computations and then filling them into this 2-dimensional matrices to do like assignment. And the second, what you're going to do is you need to convert all of the point values between the point values into the polynomial coefficients. That's how you get like a column of values and then convert them into a polynomial, which you apply, the operation you apply here is doing the FFT to do that, and then you do the IFFT to, you use IFFT to convert from point values into the polynomial coefficients, and then use FFT, or maybe like I'm wrong about that. So anyway, so like you use like these 2 operations to convert between these 2 things there. And then the next thing is like you need to do some polynomial multiplications and divisions. So those are the vector operations, which means like if you have convert your polynomial into those point values, then you just only need, what you need to do is you multiply those point values together so those are like all the vector operations. And then the fourth is like do the polynomial commitment. Here, because we're using the KZG, so we're just using the MSM operations on the elliptical curves you have, like you choose for the KZG. And the last things like you do is like open polynomial and the random points. And then one more thing is you probably run some multi-open protocols there. So those like the open polynomial at the random points is that you're given a scalar value, and then you your polynomial with all of the coefficients you have inside the polynomial, and you can calculate what the value the polynomial evaluates at a certain x you choose, at some random x you choose. So let's see what happens, what kind of computation is involved in each phases. So in the phase 1, which we do the witness assignment and then some pre-processed columns. So that kind of computation you do is witness generations and the MSM, FFT, and IFFT. So MSM, which is you need to use to commit a polynomial, and the FFT and IFFT is which you need to generate some of the, you need to convert the original columns into different values and then different coefficients. And then second, in the lookup arguments, all the computation you do, the first things you need to construct this permuted columns, which I described before. And then you also need to do the MSM and the IFFT. And the third things for the computer quotient polynomial, what you need to do, a lot of things is to do the polynomial multiplications and divisions so that you can construct this final quotient HX polynomials. And they also do some FFT here inside phase 3. And then the phase 4, which evaluates the polynomial at the random points and the random multi-open protocol, what you need to do is to do the polynomial evaluations, the multi-open protocols, and then some MSN you need to do inside phase 4. Okay, so that's all about all of the prover, what prover does in behind. So next I'm going to talk about some optimization for the zkEVM we did so far. So this is the previous graph we did. So actually there are two different types of the circuits here. So one is all of the circuits inside the zkEVM. So those circuits, they just generally have more custom gates, more lookup arguments, but fewer rows. And then another type of things is the aggregation circuit, which have more rows and then fewer custom gates and then lookups. So take an example to compare the EVM circuit we have so far, and then versus the aggregation circuit we wrote. So the EVM circuit, we use 2 to the 18 rows inside our circuit. That can handle around about 1 million gas. You can have to handle that. The gas is in that EVM gas. And then you have 116 columns inside that. But a total, you have almost 2,500 different custom gates and then 50 lookup arguments. And then the highest custom gate degree we currently have is 9. But there's also adjustable, so you can have some config. You can change it to a smaller value, 5. But currently, we just use the config as highest custom gate degree is 9. And then if you want to handle more gas inside the event circuit, then you need to have more rows. For example, if you have 2 to 19 rows, then you can probably handle 2 million gas. And then in comparison, the aggregation circuit we have is 2 to 25 rows. Because we need to aggregate all of different circuits inside one aggregating circuit. That requires do a lot of ECC operations inside the aggregation circuit. Right now we need to have the 2 to the 25 rows to aggregate all our proofs we have inside the zkEVM circuit. And then you have 23 columns and 1 custom gate, 7 lookup arguments, and then the highest custom gate degree is 5.
Haichen, we have a question.
Yeah.
So you have Brian asked if you have so many custom gates, right? Is there a selector per custom gate? Because it seems like you don't have 2,498 columns, right?
So you have share a lot of selectors across different custom gates. For example, we have one gadget, almost one gadget for each opcode, and then but inside each opcode you have different you have multiple custom gates corresponding to that gadget, and then one gadget is usually constrained by 1 or 2 selectors to constrain that custom gate. So gadget, yeah.
Yeah, it's like you implemented the opcode switching.
Yes.
Without having to use 2,500 selectors,
right.
Basically.
Yeah.
And then does that columns count also include for lookup arguments the virtual A prime T prime?
No.
Okay.
This is the original columns you have. So if you want to see so for this you will end up around 300 columns after you counting down all of the additional columns you need to have and the points you have. Okay, so now let's look at some performance numbers. So if we run this for the event circuit case study, look at example of the event circuit. So if you do the proof generation on the CPU using the Halo 2. So right now we are benchmarked on the AWS G5 12x large instance, which have 48 CPU cores and then 192 gigabytes of CPU RAM, and then there's 4 NVIDIA A10G GPUs. So if you're running like everything inside the CPUs, that's the amount of the time you need to spend in each phase, and then the total amount of time you have for the proof generation is about like 4.5 minutes to generate for the EVM circuits. And then, so the first optimization we did on top of the CPU is trying to move the MSM, FFT, IFFT into the GPU kernels, which you involve, like, for example, phase 1, you have like these things like the, so actually every phases will be involve some of the things that will be happening inside the GPU instead of inside the CPUs. And then now let's take a look at what happens after you apply this GPU kernels, where you can see like the phase 1, the most of the time is spent is on the doing the MSM or FFT stuff. And then so you can reduce that from 70 seconds to down to the under 5 seconds. And then so it counts like all of the things up. Then now the proving time is about like under 2 minutes. So you can achieve like a 2.5, 2.4x speed up. So and then this is using the 4 GPUs. So you can evenly distribute like the different FFTs into different GPUs, and then different MSM to different GPUs. So that's like utilizing all 4 GPUs on this AWS instance. And then so next things we realize is like now the bottleneck, the most time spent is in the phase 3, which is the highest time. What phase 3 does is not only the FFT, so it also does those polynomial multiplications and divisions. So it also can be very easily to be parallelized using the GPUs. So like the second thing optimization we did is to compute those quotient polynomials inside GPUs. And then so now you can see that you can halve the time you can spend in the phase 3 from 33 seconds to 28 seconds, 28.7 seconds. And then the third thing like that, so right now I think like the third thing we did is to, in the phase 2, there are certain part of things like construct the permutate columns for all the lookup arguments. That's happened like still down in the CPUs. But like if you can parallel pipeline the CPU part of the things with the GPU. So like when you construct the current, when you're doing the MSM or IFFT for the new columns you generated for this lookup argument, then at the CPU you can also to construct permutate the new columns for the next lookup argument. So I'm doing like this pipeline stuff to optimize the phase 2. And then what you get is like in the optimizing 3, you can decrease the phase 2 from 23 seconds to 5.9 seconds. And then so the total time, like now, if we want to generate the proof for the the EVM circuit is like around 58 seconds. So it's like below 1 minute. And if you compare that all the optimization we apply with the original CPU, once they achieve like almost like 5x speed up, comparing that using the CPUs. Any questions so far? Okay, so, oh wait, oh yeah. So next, like just take a look at it. For example, like, sorry, there's one question.
Yeah, sorry, and is this for proving like one, like validation of one block of transactions?
Yes.
Or, okay.
Yeah. Okay, so next, I want to look into details of like how much time you spend inside MSM and FFT, IFFT. Like if you're in the CPUs, you can think of like, you can take a look. So that almost like 64% of the total time will be spending doing like the MSM, FFT, IFFTs, which you can say like this is like some rough number there. But if you want to look at it into GPUs, right? So in the GPUs takes the latest optimization you have here. You can find like actually after you moving all of FFT and IFFT, MSM into the GPU kernels, now the total time you spend in the GPU for those operations is only like around 16% of the total proof generations. And then the rest of them actually now becomes all of the 58% of time. Although like here in the phase 3, this part of like 25 seconds is doing the polynomial multiplication divisions. That also mostly happen inside the GPUs. So but the rest of them you can see like so currently we haven't moved this like multi-open and then polynomial evaluation into the GPUs. So those part of things could be like the next target to further optimize to reduce the improve its generation time. Okay, so but like on the other case, like for the aggregation circuit, now we also did like the similar optimization to the aggregation circuit, and then now you can find actually because the aggregation circuit, the differences between the aggregation circuit versus the EVM circuit is that aggregation circuit has more rows and then fewer custom gates. Now you can find that the phase 1 takes now the most of the time in all of the proof generations. So it takes like almost like 2 minutes in the phase 1. So what happens like in the MSM and FFT, it doesn't take a lot of time. It's like almost like 2 minutes. What it's doing is doing the witness assignment. Because you have a very large circuit and you fill them like one by one row by row. So it takes a lot of time like inside the CPUs. That's saying something like we're continually optimizing and working on to improve that, to see if we find any way to parallelize this proof generation witness assignment inside the CPUs to utilize multi-cores. And then you can see like in the phase 3, which does like a lot of polynomial multiplication and divisions, that actually is less time than the EVM circuit because it has less custom gates so that you have fewer polynomial multiplications you need to do like operating in the phase 3. Okay, so there's some quick summary. We have like some takeaway we have from all of the optimization and then the comparison, like things like. So the FFT and the MSM is still like dominating time if you're using the CPUs. Although currently like we're not sure. Definitely probably we haven't heavily optimized the FFT and the MSM in the CPU. So that could be like some hand-wavy claim we have because we haven't really optimized that because we spend most of the time just optimizing the GPU kernels. So, but it could be still the case, like FFT and MSM could be dominating if you don't use the GPU kernels, but that won't be the case actually for if you have the GPUs, because it only adds up to 16% of total time. And then, so for the large circuits, the witness generation is really kind of a bottleneck for the proof generations you have. And then for different type of circuits, like you have different characteristics for different circuits. So you need to apply some different optimization to different circuits. So in the aggregating circuit, so more rows lead to higher cost of large FFTs. So you need to have better large FFT kernels in the GPU. And then EVM circuit actually has lots of custom gates, so that you need to do better polynomial multiplications and probably polynomial evaluations better to do that. And then so that you need to tune the performance based on different circuits layout. Okay, so previous is all about our the proof optimization we did so far. And then we'll continue working on that. So next, I'm just going to talk about how we want to build our decentralized proven network. Yeah, so this is the kind of the architecture I showed before. So we have this decentralized proven network so that everyone can join and build that. But how we are going to reach to that goal, like the final goal there. So I think right now, what we're doing like in the stage 1 is that we build a GPU solution for generate proof of the zkEVM circuits. And then we're going to build so right now we're using some AWS instances for the proof generations, but we'll also build some private GPU clusters to provide a more stable and then cheaper solutions for building for the proof generation power on our testnet in the stage 1. But the next stage we're going to do is we're trying to collaborate with some hardware partners and companies, and then to see how we can share our results so far, and then share our proof systems and our optimization some profile we did, and then to see how we can work with them together to build a better customized hardware accelerators. And I would believe that with better custom provers, it can still can improve, shorten the proof generation time. With you can see how we can do better parallelize on the rest of part we currently spend in the CPUs, and then how to make the MSM and FFT even faster than the GPUs. And then at the stage 3, our plan is going to definitely open source our GPU provers we have so far, and then probably we'll have some add up a little bit more optimizations with some permissionless license so that everyone can use as some baseline, so you can run the GPU server yourselves to become our prover, a roller to join our decentralized network. And then, so if like at that time we see like if there's some solutions from the hardware company, so that people can also buy those custom hardware from those hardware companies, and then to use that as their provers in parallel. So yeah, so that's pretty much like what I want to say about our decentralized prover networks. And then thank you. If you have any questions. Oh.
Many of the hardware accelerator vendors are working on improving FFT and MSM performance, but according to your result, they only account for a small portion of your time spent. So do you think that their improvements will actually improve the overall proving time?
So as I said, like so right now we found like the MSM and FFT. So for the smaller circuit, definitely they're a small part of that. But I think like for the larger circuit, they will be still there's room to improve for the very large circuit. So if you have very large number of rows, you can still improve that. But definitely there will be also some solutions you can think of like to better parallelize the rest of part, like which you involve inside the proof generations.
For the time management of your rest, because it's a time management, is your GPU fully occupied? Because it could be bottleneck on the memory communication.
Actually, it's not fully occupied. Definitely, there's sometimes, like for example, I think inside aggregation circuit, sometimes the FFT will be waiting for the CPUs because CPU takes more time to generate those permitted lookup new columns for the lookup arguments. So that sometimes GPU are waiting for that columns to be generated before they can start working on the FFT and the IFFT.
Is there a way you can just like? I'm trying to formalize my my question here. So your current gas limit is like comparatively small compared to like L1, right?
Mm-hmm.
But since you have the aggregation circuit design, is there a way to just say like, okay, we're gonna have a lot of blocks, but each block is gonna have a very small amount of gas, and then really lean on the aggregation circuit to kind of just aggregate all the inputs?
Yeah, we can definitely do that. We're also planning to do that. It's working towards to that.
So
and also, there's like also plans to have different size of circuits so that you can have larger circuit to handle blocks with more gas cost you have, and then for a smaller box you can have smaller circuits. So.
I see. So do you envision having like a pretty strict gas limit for the near future?
I think we'll be still flexible. So we're trying to see like if we have like very fast blocks, and then you can have you don't need to put out like a very strict gas cost. If you have like more stuff like you have, you can just use larger circuits. Probably there's definitely some limit of the maximum you have, depends on circuits. There will be some limit there, but it will be quite flexible, I would think.
In a world where you have like a decentralized network of sequencers and provers, have you thought at all about like MEV on layer 2?
Yeah, this is kind of an interesting topic. It's we're working with like all of the researchers working on the MEV, and I think like there's also some talk at today's MEV workshop, talking especially for the layer 2 MEV. I think there will be some interesting topics we're going to explore.
I did not know that witness generation was such a bottleneck for large circuits. I guess it makes sense. But could you break down like which part of witness generation is taking the most time?
For that, I don't have specific number for that. But actually, we also noticed like one thing is like if you're using this dual pass layouter, it has to add more time for the witness generation because you need to go past the circuit twice. So it takes more time. And also, because you have the region stuff, you also need to at least go past like twice for the proof generation because you need to first generate all the regions and then to lay out that. So that could be like one issue that you need to go through like all of it.
Like you said, we should try and parallelize it.
Yeah.
And one abstraction along which we could parallelize could be regions.
Yeah.
Because each region is pretty self-contained.
Yeah, but sometimes it's not so naive to parallelize this thing because the witness generation could be depending on, so if it's step by step or row by row, the next row value could be depending on the previous row's results so that you can generate the value you want to put into the next row. So it's not very like naive, like a straightforward solution, a general solution for at all. But maybe for certain circuits, you can have ways so you can predict, for example, how many, what's the value you're going to do, or kind of like a trunk by trunk. You can do this within the trunk. You do the sequential things, but in parallel, you can do the witness assignment for different trunks.
Yeah, I think this is an interesting problem, like in general, and maybe we could think of some best practices for which to like write your witness generation to be easily parallelizable.
Yep.
So before sequencer decentralization, how do you think of that, and like how do you think of like distributing the problem, if any?
I think we haven't like finalized all of the details of how the tokenomics stuff. So I think like just don't have a very concrete answer to that.
In the decentralized network, are you planning on holding the block time back so that your GPU solvers, GPU provers can keep up?
Yeah, actually, we're working on like that to packing multiple blocks into a single EVM circuit, so that you can, because sometimes like what happens like in the testnet is like usually most blocks just have one transactions. You don't use all of the circuit space you have. So one way to improve is to pack multiple blocks inside a single circuit, so that you can have even faster block time inside the layer 2s.
Are you planning on capitalizing on ability of GPUs after merge?
We'll see. Like we'll see how it goes. Like with after the merge. Okay, so if there's no more questions, actually for the rest of the time we're just doing some Q&As, like not probably related to this, but if more general questions you have, to me or Sandy or Mason.
Kind of curious to hear more about like how do you expect the UX to be like with commitment and finalization? Like if the difference, I don't know, is it like on the order of 1 minute or 1 hour or 1 day? And then like do you expect users to just like trust the committed ones or like
Yeah, I think so. So user like I feel like it just I think for some small transactions it should be like probably you can directly act on top of the pre-committed, maybe like if it trusted the sequencer, or like and then I think for the commitment usually happens probably in minutes to be from the pre-committed to committed, and then for the finalizing to a block of finalized probably I think can be like I think we still haven't decided how much like also that also depends on how much gas cost you need to pay for the finalization for the proof. So this is kind of a trade-off. If you have longer finalized time, so that gas cost and the cost on the layer 2 will be cheaper because you can aggregate more across different transactions, so that the final proof verification on the layer 1 will be cheaper and amortized across more transactions. But you have shorter ones, then you can probably the transaction fee will be slightly higher. So it's kind of like a trick you can play with different things. But I think probably like an hour or two, like could be like a reasonable range. But it's still like I haven't decided to finalize those details yet. Yeah.
And then the L1 gas cost that you pay, is that just like an estimate of what those will be basically?
Yeah, so
the gas price itself can change also.
Yeah, the gas price could change vary a lot. So definitely there's some like prediction. So there are two parts of the layer 2 cost. One probably is like three parts. One part is the layer 2 operation cost, where we prove like you pay the electricity to generate those proofs. And then the second part will be the data you want to roll up into the layer 1s. And then the third part will be the validity proof verification on the layer 1s. So I think so far before the proto-dank sharding or dank sharding, the second part, which the data availability, will cost more, takes more percent of the part inside your layer 2 transaction cost. And then, but like after the proto-dank sharding, so you can think like probably that the cost of to roll up data will basically be free. Then you can think of like how to optimize the verification cost on the layer 1. Yeah. Okay.
So in an ideal scenario, is before authority, L2, the bottleneck becomes essentially gas execution, right?
Yes. Oh, I haven't like the. So I think we did some benchmark, like definitely a few thousand transactions per second. But I think that's probably some ERC20 transfer or like just native transfer. Yeah, like the easy can reach a few thousand transactions per second. But yeah, there are definitely some places you can improve for the GoECM because the GoECM is not designed to be very efficient to process like a very high transaction, like the high throughput. So there are definitely room to improve the GoECM to be handle even higher transaction per second, like a higher throughput to do that. But yeah, I think it will be pretty high, like given the current situations. But definitely we can also improve on that. Yeah, yeah. Yeah, actually, so this is like something we consider, like also look at some Aragon or like some other implementations, but it's not the top priority at the moment because we haven't like hit to that bottleneck yet, bottleneck by the sequencer yet. So, yeah.
Are your bridge nodes and contracts specialized in any way, or are they kind of derived, or are they forked from existing projects?
For what? Sorry.
Are they forked from existing projects?
It will be permissionless for the bridge. Sorry.
Like,
yeah.
Are your bridge nodes and contracts, do they work differently from sort of existing bridge designs, or are they kind of forked from some existing model?
I think I just follow some existing standard model for the bridge. Yeah.
I have two questions, but they're sort of the same. Because like, if you had an adversary who wanted to hurt you the most in terms of proof of performance, what sort of transactions did they want to create? Do you have an idea what your gas pricing model will look like? What would gas prices look like in this proof system?
Yeah, I think the attacks. One attack we thought about is you can use a lot of extend code hash or code size. That's relatively like cheap operations, but you need to load the whole contract into your bytecode table. That could be like easily to eat up all of your circuit space. It could be like constrained by how many contracts you can load in the bytecode table, and also you need to compute the code hash given all the bytecode. So that could be like a one attack. So we're trying to think some way like we can maybe adjust the gas price or making some optimization how to compute the code hash. So kind of like way to improve that to avoid those attacks.
Your current idea is to keep the same gas prices as your mainnet.
Yeah, we try to keep as same as like as close as to the current Ethereum gas model, so that we don't like change a lot of developer experience like from things. And then there could be also some extra security concern if we change the gas model, so that if you don't attack the circuit, you can probably attack the sequencer like the side. Oh, sorry, what was the second question? Like.
No, that was the gas model.
Oh yeah, yeah, like yeah, that's what I was answering. Okay, so if there are no more questions, we can end our workshop. So, and thank you very much to everyone who come and then join our workshop. Thank you so much.